All right, here we go. Modern physics. This is the last unit of the course, and it is a like a buffet of topics in modern physics. There's absolutely no depth. I mean, I feel silly when I write down, "Oh, we're going to study, general relativity and quantum physics on this day." I mean, these are, courses upon courses of university study, but all I'm trying to give you is an overview of what things are. And even though these are really hard topics, because I can only touch the surface of them, then, sort of the nice thing for you is you walk away with, like a little idea of the different things. But also, I can't make the questions very hard either, right? Almost all the questions require a level of math you don't have, so I can pick and choose what questions we can do, and and again, it's just to play with it. But there's some cool things we learn in this unit. Chose this picture because it's not very modern, but really this is, from relatively, let's throw that term out. This is modern physics, and here of course is Albert Einstein. This is in 1921, so this is after general relativity, which is really his stronghold on, I am an important man in physics, right? This is Max Planck. We'll talk about Max Planck. I won't be able to. This is Werner Heisenberg. Of course, we'll talk about Heisenberg. You know Werner from Breaking Bad. We talk about sort of what the work that he did. Where's Niels Bohr? We'll talk a bit about Bohr. There he is. There's Niels Bohr. So these and this is Marie Curie, the only female in the bunch. Marie Curie. Albert Einstein really liked this lady. She, of course, did a lot of study on radiation, and she died of cancer. Sort of specifically connected to her study. I think her husband did too. I don't know if that's her husband or not, but anyway. So these are the modern physicists, and this picture was taken in 1921. And I'd still say the topics that they opened the door to is where all physics is headed right now, because I think you've seen it. You might have seen the quote. I have had it up in my room. Of 1895, Lord Kelvin said, "Physics is done. We know everything. We know everything about classical physics." That's what they didn't call it then. They just called that physics. And then it was sort of with Einstein and then this guy Max Planck. They really started opening the door to this idea of everything that's modern physics, which I think of as particle physics, which is kind of like quantum physics, the same thing. Quantum physics, particle physics, relativity, all these things that came after. But classical physics, which is the physics that we generally have, only thing we've studied up to this point, besides maybe Young's experiment, was borderline. It's funny, the only topic in classical physics actually that's not really been studied, and physicists say still requires further study, is turbulent water flow, which we don't talk about that in this course. The grade 12 college prep course talks about it a tiny bit, but it's basically the only thing that's that can't be calculated very nicely. That's just a regular large scale physics sort of thing, is turbulent water flow. Everything else is completely understood, and I've told you this before, understood to the point that we could get to the moon with that level of understanding, right? All the stuff that happened here, is sort of understanding. Is understanding much deeper things that we need for our electronics and such. But if you take electrical engineering, for example, you'd study some modern physics. As a chemical engineer, I hardly studied it, barely talked about it in university. So my level of understanding is only really developed as for my love of the game and just from being alive, but not from my engineering study. Anyway, oh, here it is, Lord Kelvin. There it is. He says, there's nothing more to discover, just more and more precise measurement. So that's true as far as classical was, except for laminar flow. But so the first topic we're going to study is Albert Einstein. Whoopsie, that stunk. Did I lose it? I lost it. One sec. There we go. Is the special theory of relativity. And he basically came up with two main theories of relativity. The first in 1905 was with a special theory. And the second was in 1914, and it was the general theory. It was the general theory that changed the playing field a lot for physicists, though only on a theoretical plane, not on a practical plane. But we'll talk about that later. Special theory, however, it's pretty unbelievable. So the special theory of relativity is E equals mc squared, by the way. It's the first 3 days of this unit. This is this is him trying to describe it, okay? And I probably told you that before, this idea that time is relative. And really think how revolutionary this special theory was. I mean, he wasn't working as a physicist. He wasn't, I hate to say it, but he wasn't good enough. I'm quoting my fingers right now. I have the two little bunny ear fingers saying he wasn't good enough to get a really good job in physics. And so he wasn't doing that, but he was thinking about physics. And I've told you this about Einstein, or I probably have told you about Einstein, that he never did any experiments at all. There's this I call it an old wives' tale that Einstein failed mathematics in university. That's a lie. That's not true. He did fail a course in university though, and it was a lab course. He didn't like labs. He considers himself. He has one of his famous quotes is, "Don't worry about your challenges in math. Mine are still greater." He could do some math. He could do some math like you and I wouldn't believe, but he found that his level of understanding math wasn't good enough for the general theory of relativity, and he had to hire someone to do the math for him. But let me just say, it was way beyond any math, that we could manage. When he was 12 or 13 years old, he came up with a proof of Pythagorean theorem. That was just something he did because he was curious. Anyway. He's awesome. You should read his book. Well, this book, not his book, a really nice biography on him by Walter Isaacson. It was good. Okay. Yeah. So here's the weird thing about special theory of relativity, and so he came up with this as a complete unknown, as someone with no credibility at all. Yet everything and with no lab experiment, no experimentation. He walked out and said, "Oh, time isn't absolute, it's relative. Depending on where you are, time passes at a different rate." I mean, that's a huge thing. In fact, Isaac Newton said the exact opposite. And Isaac Newton, at this point especially, still now, but back then, was seen as the king of physics. He was the physics king, right? You think about Newton's laws of motion, the calculus, like all that he did, right? Gravity, gravitation, and Albert Einstein, right away said, while Newton said time is an absolute, he said no, it's not, and these are the reasons why. And we'll get into that. Yeah, just a couple quotes though. This idea of him defining common sense as prejudices that you acquired at an early age. So everything that we talk about with special theory feels a bit wrong, and that's a lot the same as a lot of modern physics. Quantum physics is the same, and so when I'm going to get you to watch this a little bit on string theory at some point. And it blows your mind. Things that, at least as far as we know, they're true, even though they don't make any sense. That's physics. For me, that's physics gets to be a little less fun at that point. Anyway, so here's the two main postulates of special theory of relativity. The first is that motion is relative, and I don't know if you've ever had this when you're driving and you're on the highway. I don't know, like say you see someone zoom by you, or you're kind of sleeping or something, you open your eyes, you see someone zoom by you, it almost feels like, am I going backwards? Right? Or or vice versa, you zoom by someone else, you look to the side, it looks like they're going backwards. That might be a better idea of relativity, right? And that's all it is. That's all Einstein was saying here, is that, depending on how fast you're going, if you're this van, you see that airplane is going backwards, which of course isn't true. The airplane's just not keeping up. And then the second thing, that and I use the word, I don't use the word postulate. Someone smarter than me came up with the word postulate. Postulate just means, these are the main starting points. And then everything that came after is sort of based, if these two things are true, if we can accept these two things to be true, then everything Einstein did afterwards with special theory, it's like the starting point of the argument. and then we're accepting that to be true, and then he developed the theory sort of using those as the basis, which might make you say, well, how do we know this is true then? The speed of light is absolute, and meaning that this is it. Light goes this speed, and it does not change. Well, it does change when it goes in different mediums, but it can't go faster. Nothing can go faster than the speed of light. And it's just, there's sort of lots and lots of experimentation to show that now. And I've probably told you this before too, that when James Clerk Maxwell developed the equations related to electromagnetic fields, you know, Einstein said this in 1905. Maxwell was a little bit before that, but he had come up with the speed of electromagnetic field, and it came out to be this number. They're the same thing, right? Which of course makes sense because light is an electromagnetic wave. Anyway, moving on. I think I'm moving on. There we go. Okay, so let's look at the first postulate. So all motion is relative. That's, you know, I think it's easy to understand that. You know, this is the way we talk about it in the physics way of saying it, is that all Newtonian physics is valid if you are in an inertial frame of reference. And I'm going to explain to you what an inertial frame of reference means. First of all, just frame of reference, and it's just a viewpoint. So again, from the van's frame of reference, the plane appears to be going east. That's if the van's going really fast, 300 kilometers per hour, and the plane's going 200 kilometers per hour. From the frame of reference of the van, the plane is going backwards, right, at 100 kilometers per hour. From the frame of reference of the plane, well, the plane doesn't really think he's going anywhere. If you're going at a constant speed, you kind of just think you're traveling 0 and everything else is moving around you. And then if you're someone on the side of the road, the plane appears to be going 200. So we usually use the frame of reference of the Earth. However, what Einstein said, and kind of just makes sense, this is where physics and philosophy just cross over, right? Because it's all true, it's just also just language. You know, if you're all these things are equally correct. We usually use the frame of reference of the Earth, right? Which, so from our point of view, the plane's going 200 kilometers per hour west, the van's going 300 kilometers per hour west, period. You don't often use another frame of reference. So that's the frame of reference part. Now remember, we're talking about inertial frames of reference. So what does that mean? Okay. The inertia part, just remember from Newton's first law, an object at rest will stay at rest, or an object in motion will stay in motion unless acted upon by an outside force. So that's inertia, right? And it kind of means that if you're in an inertial frame of reference, you're either at rest or in uniform motion. So to give you an idea, if you're sitting in your car and you got your dice hanging from the rear view window, you say, okay, well, what forces are acting on the dice? Well, you know, there's the tension of this rope up, there's gravity down. That's nothing to do with frames of reference, but that's just, we're looking at it, we're sitting still, the physics makes sense on these dice. We could calculate anything we want about these dice, right? Because we know Newtonian physics. Now, from your point of view, you're sitting in there in your driver's seat, you hit the gas pedal, and think about it. What you notice is, it looks like the dice are coming towards your face, right? It's almost like the dice, if they're a long enough string, they can almost hit you in the face, right? I guess they'd have to be right in front of you, but, you know, say you're in the middle. So it seems like there's no force causing them to move towards you, right? So from your point of view, these dice are coming towards you. Remember, from your point of view, usually you're not moving. You think, you know, it's like everything's moving around you and everything's with reference to you. So it just doesn't make sense. It doesn't make sense. And this is all like what you are. If you start accelerating, you're no longer in an inertial reference frame. You're accelerating, and therefore physics that we understand, Newtonian physics, is uncalculable. Like you can't do anything with it. Like how do you calculate the rate at which from your point of view, like why are these dice coming at my face? There's no physics reason for that if you use your point of view as the frame of reference. And that's what we call a non-inertial reference frame. So you can only really do physics if you're in an inertial reference frame. You're staying still with reference, you know, you're not accelerating. More importantly, you're not accelerating. So if Kirk's standing on the side of the road, this video is getting long, sorry, too much chit-chat. Kirk's standing at the side of the road. What he sees, keeping in mind he's an inertial reference frame, he's going to look at your car as you start to accelerate, and he's going to see these dice. But what does he see? He sees that the dice remain stationary until the car pulls them forward. That's why they appear to go towards your face, because the car pushes you forward, and so the dice appear to go backwards. But as soon as the dice, this just takes a second for the dice to catch up because of where they're connected, right? So the dice remain stationary. So is this in conflict? No. So Kirk is in uniform motion, and so he is an inertial reference frame. So physics makes sense. Things make sense for him. So all Einstein was saying when he talked about, inertial reference frames, is that, and that Newtonian physics that we can calculate and understand, only makes sense if you're using a frame of reference of someone not accelerating. Okay? Nice car. So, inertial reference frame means no acceleration. So his special theory of relativity is only valid when there's no acceleration. And so where things got really, crazy, by the way, is when he did his general theory. That's why it took him so long, and he needed help with the math, because there he was using non-inertial reference frames. That's a little hint of what's coming. So one thing he said too is that we can't tell the difference between not moving and moving at uniform velocity. Well, there's a great little video you'll see. Never mind. And we only study Newtonian physics in inertial reference frame. I think this would be. Oh yeah. So this idea. So we can only use Newtonian physics in an inertial, which means uniform velocity or not moving. But we calculate acceleration all the time. But we're calculating them from the point of view of someone standing still. Usually you calculate the acceleration of the car because you're measuring its motion, excuse me, from the point of view of someone sitting on the side of the road, what they see. And remember when we talked about centrifugal force in circular motion? And this is kind of the same idea. Like someone sort of made up centrifugal force so that we could explain the non-inertial reference frame of circular motion, right? Because obviously when you're constantly accelerating around a circle, you're no longer in an inertial reference frame. So something had to be made up to understand it, and that was what centrifugal force is. Okay, this guy's getting to watch the first 3 minutes, and then we'll shut this video off.
The bizarre consequences of special relativity arise from two postulates, two things which, once accepted, lead to Einstein's space-time. In this series of 5 episodes, we will introduce and build upon these postulates to derive the consequences of special relativity. So, are you ready? Okay then. Fasten your safety belt and prepare for takeoff. Imagine you're waiting on the runway and decide to take a nap. When you awake, all the window shades are drawn and no one is in the cabin. So, can you determine without peeking out the window whether or not you're on the tarmac or flying in a straight line at a constant speed? You might think that dropping something would help, but it doesn't. Some people reason that if they drop something and it falls straight down, they aren't moving. But really, all this does is establish that they aren't accelerated. This is sometimes known as Galilean relativity, and it's why we don't perceive the Earth's rotation. For a sailor traveling at a constant speed in a straight line, a cannonball dropped from the crow's nest falls straight down. To a landlocked observer, however, both the ball and the ship are moving forward, and so the ball is seen to follow in line. This means dropping something can't tell you if you're moving. It looks the same to you either way, as long as you're undergoing uniform motion. Now, if the plane was to suddenly speed up after you released the bag of peanuts, then it wouldn't land directly below your hand. However, this is what's special about special relativity. We are concerned only with things standing still or moving in straight lines at a constant speed, what we call uniform motion. This introduces the first postulate. There is no experiment you can perform to determine if you are standing still or moving in a straight line at a constant speed. Yes, you could have looked out the windows, but all you could have said for sure is that the ground and the earth were moving relative to each other. The plane could be the still one, with the earth rotating below. It's all a matter of perspective. It's all relative. All right then. Are we happy with the first postulate? The most one can say is that she is not speeding up, slowing down, or changing direction. She cannot say whether this is because she is standing still or moving at a constant speed in a straight line. It might help to consider that there is no absolute reference frame in the universe with which to compare one's motion. Remember, the Earth is hurtling around the Sun, and the Sun around the center of the Milky Way. The best we can say is, I'm moving relative to this or to that. Okay then, let's go to a parade.
Okay, we'll come back to that. And that's the end of the first video. It's a long one, sorry.